Hi and welcome. This time around we have a relatively quick project involving just a few parts. We're going to be making a burnishing tool for the lathe. And a burnishing tool is basically a tool that rubs on the part and compresses the surface of the material. And I think it makes it harder, at least locally and for a very thin thickness, cross-sectional thickness. But I think primarily it makes a very smooth finish. That's the point of it. They use a lot inside of cylinders and things like that. After you hone them, you can burnish them. They sell burnishing tools that have little roller bearings that press against the outside and make the finish smoother. So I'm going to try it here on the lathe, and I got the idea originally from Jim over at Tangent Engineering. The YouTube site is Tangent Jim, and he's actually got a lot of really cool content, and he's got a lot of really innovative things he sells. So go check it out. Check out his channel. So the parts here are pretty simple. We got a ball bearing, and we've got a bearing race, and the ball bearing will ride on the bearing race as it rotates. The bearing will provide the ability to support the ball bearings push forward and still rotate. And then the side-to-side rotation will be one of these bronze bushings here, which I will have to bore out to 5/8. Originally I was going to use 1/2 inch, but I can support 5/8 just barely with this bushing, and I think that'll work better. I think the larger diameter will help, although that decreases your force per unit area, so you might need to push harder. So it's sort of a balancing act. Maybe 1/2 inch is better, I don't know. But we're going to try it this way with the 5/8. By the way, Jim over at Tangent Engineering also will send you free plans if you just send him an email, so that's pretty cool. I'm not following his design exactly, although fairly closely. So if you're looking to do the same thing, save yourself some time and use Jim's plans for you. One thing on mine that is originally going to be different, I was originally going to use roller bearings. This is ball bearings, sealed ball bearings, which I think sealed bearings probably are needed on the lathe. Open cage, which rotate a lot more freely, would let too much grit in, and I think that might be a problem. Maybe I'm wrong there, but so I got sealed or shielded bearings here. I originally got roller bearings, but they're so stiff, they don't want to roll very easily, that I'm worried that the ball bearing would just sit in one position and not actually rotate on them. So that's why I opted for the ball bearings instead. So we're going to go that route. Originally I thought roller bearings would be better because they can handle a lot more radial force here, which is where we're pushing. The dynamic load is going to be fairly high on this because you're trying to push the ball bearing into the material to flatten it off. In any case, got some material. I cut it to rough size here, and we're going to take it over the mill and get it to dimension and then just get going. Next up, I need to dimension this stock, and normally you put a parallel on one side, you pop this guy in here and support the moving jaw with a piece of aluminum so that it could deform. Since this side's not known square, you'd cut one face, then you'd flip that face towards the fixed jaw, put this aluminum back in, tighten it down, do the top, flip it 180, do the bottom, then do the back finally, and then do the two sides. Well, I've got a new approach, but it involves taking off the vice jaws. And what I find really annoying about taking off the vice jaws is, here's my Allen key. In order to get this Allen key in here, I've got to open my jaws all the way up. And I thought, it'd be handy if I made just a little adapter that I could open the jaws up a couple inches and fit the Allen key in there, maybe break it loose with this guy or the tool itself, and then just spin the Allen head screws in by hand. And then maybe give them a final cinch up with this or something like it. So let's over the lathe and make that tool. We're going to do a side trip before we dimension this stock. Because the way I want to dimension this stock, you actually get to do 5 sides all with the same setup without touching and moving this part, which is really awesome. CNC guys do it all the time, but we don't as manual machinists do it anywhere near as often. And then when you're finally done, you deck the final side off to dimension and you end up with a very square part. So let's make the Allen key first. All right, so here's the plan. I got a nice piece of stainless here, and I'm just going to drill a hole down the center of this. Originally, I had laid out to mill the hex out of the middle. I was going to drill the corner sections out with a 1/16 inch drill bit in each of the 6 corners. Then I was going to mill the flats. I was going to drill most of the center material out, which I still could do, which make a much tighter fit since the Allen key is not actually 0.375, it's like 0.372. But it turns out I have a rotary broach of 0.375, and I want to use it. So it'll be a little sloppier, but I'm going to add some epoxy in there to hold it in place anyhow. So what the heck, let's give it a shot. So I got a 3D printer somewhat recently, and I used to keep all of my center drills in just a box sitting on top of the lathe, but I decided to print up something that would let me store some stuff more conveniently. I've got a scribe here and an Allen wrench that goes with some of my inserts. Center drills is one of my inserts that I swap out. This is a non-positive rake diamond, and I have the aluminum one in there right now. It holds the angle guide for threading and some countersinks and a center drill. It was a quick job, and I could modify it to hold some other stuff later, but I thought it'd be pretty cool and pretty simple. If anyone needs this 3D drawing, 3D layout STL file, I can send it to you. So just let me know. By the way, in case you're wondering, this is a lure lock needle with a really long needle, stainless steel. Got these off of Amazon. They're great for getting coolant in deep in spots. Next up, start the lathe, run the rotary broach in. This is a pretty big broach, and I think I was supposed to drill the hole beyond 3/8, but I wanted my edges to be square, so that's part of the problem. Is I think I'm taking more material out than it was designed to do. Yeah, so I need to drill the hole oversized. One problem I have is that this broach is actually designed for softer materials, and this is stainless. This might not work. Although it seems to be going in. Keep my fingers crossed. That seemed to work pretty well. I hope it actually worked. We'll have to stop the lathe and see. Oh, look at that. It did work. Here's a spare Allen key. I always save the material. Oh, look at that. That is a really nice fit. Oh, that's going to be great. Okay, we'll be able to glue this guy in. So this is a pretty handy tool to have. They can be, the broaches are very expensive, although I found a kit that had everything included, and I don't regret purchasing it at all. I kind of stressed this by doing stainless, so you can already tell there's a little wear on here. Maybe that stainless wearing off. Still feels sharp, but this is mostly for soft materials like mild steel. I could have probably gotten away with 303 stainless. This is 304 because that's what I had, so I was kind of pushing it, but it went in pretty well. You'll notice there's a rather substantial lead-in chamfer. You're supposed to do that to lead the broach in. So I'm going to face off some of this material, clean up the outside. Just going to clean up the face, remove some of that excess chamfer. That's looking good. Okay, I cleaned it up, but I didn't need to clean it up that much now because I'd like to knurl it, although I don't know if my knurler is going to fit in there. I didn't think about that aspect. Might need the part to be sticking out further. I guess we'll find out. It's really tight in here because this piece was so small, so knurling it's going to be a bit challenging, but we're going to give it a shot. Got the lathe slowed way down. Got some cutting fluid there. This is a clamp style knurler. I think one of the next projects, I got to build a better knurling tool. This one just flops all over the place. It's way too sloppy. And as a result, I don't think I'm going to get a very good knurl out of this. I'm not happy with the results of the knurl here. They're very uneven and there's all kinds of crap in there. I'm not happy with the results of that knurler. So I'm just gonna take off a little bit of material here since that diameter doesn't really matter. We're gonna knurl again. This time we're gonna use a push knurler, and I'm gonna go for a much coarser knurl. See how this works. I don't like push knurlers because it puts all the force back on your cross slide, so it's not very healthy for it. But I don't have a choice because the clamp one I've got sucks, so we'll definitely have to build another one. Here we are for round 2. We got the speed slowed down a ton. That's a great sound I've discovered there. That's one hell of a coarse knurl too. So we're doing a pass, tightening it in a little more, going back the other way. We'll do this a few times. I don't think I'll be able to get as deep as the knurls are on there. It's kind of a horrible sound it's making. I've put a lot of pressure on the bearings and the cross slide. I can tell you I don't feel anything deep, so I don't think I'm able to apply enough force. That's why I like the clamping knurls much better, because you can really crank on them and get some force on the part. Oh, that's better than I thought. That's much deeper. All right, that'll work. I did not think that was working at all. It didn't feel like it, but these are actually quite deep. All right, so now we're gonna clean this guy up. And I'll try and figure out where I want to cut this guy off. It might be based on where I can get this guy to fit. All right, that will be it. And I'm going to run one quick pass over the top of this. Oh, that's actually really good. Yeah, it really catches your hand nicely. Just doing a real quick cleanup pass across the tops of these to make them all even and fairly smooth. Pretty hard on that insert because that's an aluminum cutting insert, very positive rake. But I find if you take tiny bites like that was 5/1000 pass. Well, that took off more of the knurl than I expected, but you still can get a good grip on it. That's kind of surprising. This is an interesting learning experience. Cut off a bit of hex key stock that I had and epoxied it in place. Hey, Nairobi. There's your puppy tags, Nairobi and Cairo. All right, so now, instead of having to open the jaws almost to their full extent, I can just pop this tool in here and remove the Allen bolts. This is much nicer than opening the jaws all the way, which takes forever. I don't know why little things like that bug me, because it's not really that big a deal. It's just annoying. In any case, you can pop the original jaws off, and I'm going to sub in some Mighty Bites. The reason I'm using the Mighty Bites will become apparent shortly. Makes going in a lot easier too. I already appreciate this tool, as simple and as silly as it is. Give them a snug. Now I can grab the stock by the bottom 1/10 of an inch, I think. And I can come and machine these 4 sides and the top all at one time, which means I'm machining 5 out of 6 sides all with the same setup, so everything relative to each other should be pretty darn close to perfect. All right, so first we're going to clean up the top. I'm leaving all the excess on the bottom. This material is 1.1 by 1.1, and it needs to be 1 by 0.9, so I'm leaving the extra 0.1 on 0.2 on the bottom, which will hopefully let me get past this Mighty Bite part, so when I do the final pass to remove everything off the bottom, we'll be good. Got to take 200 thousandths off. We're going to do a 10 thousandths pass. All right, so I set my depth for the cutter to be just barely above these little cleats that are holding this part in place. So now I can just go all the way around the part and get the remaining 4 sides. And all I want to do is clean these up. I don't actually have any absolute dimensions for this part. So we can call that cleaned up. That'll be good. And I used a Weldon flat so it wouldn't pull the end mill out, but it looks like it went down just a tiny bit because it started to cut into this guy. We're just going to skim off the back and then dimension the front completely. Here's 50 thousandths, might be a bit aggressive. 200 RPM. Slow feed rate. That was climb milling for a 50 thousandths pass, great finish. Now we're going to do conventional milling at 50 thousandths. I think climb milling's better finish. That's why we'll do my last finish pass with climb milling. I could have chosen to take off of each side symmetrically, but I decided to clean up the back and then just do a straight pass on the front. Ooh. A little noisier with conventional milling, and we're coming back for finishing pass. Shouldn't have a lot of chatter on this finish pass because we're only taking off about 7 thousandths. We're back to climb milling because it produces a better finish. Now, don't think that this solution provides you a free pass, because if the nod of the mill, if this like this or like this side is not going to cut square, it's going to cut a parallelogram, but at least it'll be equidistant at any one point. But you get it, if it's tilted like this side will in cut on the bottom and this side will leave extra material on the bottom. So it's not perfect by any stretch. You still have to have your mill trimmed in pretty well.